I have also not managed to remove that marker here. Okay. So, but now I think we can go on. I trust you're all back. Any indication? Raised virtual hands, thumbs, whatever. Okay. Oh, great. That's two of you. That's enough. So we talk more about the storage end, storage daemon configuration, here the device configuration, and now in particular what to do if we need to do data spooling. Alexander mentioned before that that data spooling has in general the effect that well, which is the definition of the term, I think, to collect the data temporarily and to collect it as it comes in and only to write it to its final destination later on. One of the reasons you want to do that is to ensure that you are making good and efficient use of tape drives again. Tape drives are a bit particular here compared or in, compared to disk systems. Of course, tapes with their well hardware-based sequential writing, they need data flowing to them at a reasonable speed to actually be able to write. And if you have data coming in too slowly, you end up writing small blocks of data, repositioning the tape all the time, wasting lots of time and putting extra strain on both the tape drive and the tape cartridge as well. So you try to avoid that, and avoiding that can be done by just, well, gathering as much data as possible as it comes in on the storage daemon, and then write it to its final destination on tape in larger chunks. This is one reason why you want to do spooling. Another reason to do spooling, which is also not strictly useful for tape systems, but also for other storage systems, has been implied or has been indicated that it could be interesting by Alexander yesterday, because if you have a job that fails while it is running a backup, and the backup data is already on the final destination, we are using potentially rather valuable storage capacity for jobs data that we will not need because we may not want to be able to restore from failed jobs or from incomplete jobs. And of course, if we have a job failing, then if we do want to make sure that we're not blocking storage capacity by that job, we can use spooling, and the result would be if a job fails and has spooled data, we are just throwing away the spooled data from its spooling space, from its temporary location, and we're not using final storage destination capacity, which can be an advantage. So as it turns out, in particular, if you have many jobs that you expect can fail, it may be useful to use spooling with those jobs. Happens, for example, with workstations or laptops that you're backing up of end users where essentially you don't know if they are just shutting down their computer while backups are running because they do not even need to know about backups. And in that case, spooling can save you a bit of storage capacity in the end. No matter what we do, spooling needs to be configured. By default, the storage daemon will not spool data for jobs. You need to enable that per job actually as well. And we need to have the storage daemon configured to know how to do spooling. And for that purpose, of course, one of the most important things is we need a location to put the spooled data. That location is defined by the spool directory directive in the device configuration. You need to do that for every device, and you point it to a directory on the storage daemon host. Now this directory should be on a dedicated file system. It should not be on the file system you use for the operating system itself or anything, simply because we want this file system to become full. Not probably 100% full, but we want to fill it reasonably well, because that's the whole use. We also need to make sure that we have good throughput there. I mean, not necessarily for the example of the laptops we're backing up, but if we want to spool data and really be able to saturate tape drives while putting this spooled data to its final destination, we may need a storage location with pretty exceptionally high throughput requirements. Well, for a single tape drive today, you can achieve a file system where you can read data as fast as you can write to tape. But imagine that you have a tape library with several tape drives, like 4 or 6 or 8 tape drives, each of them expecting a pretty decent throughput when you write to them and you want to saturate them. And probably you need to, or you want to share the spool directory for all those devices, just to make sure that you are making really best use of the available capacity. Well, then we need a storage system, a file system, where we can actually read data with the multiple of the throughput that we need to saturate all the tape drives. And that can be a lot. We also want to be able that at the same time that we read data from the spool area, we can still write to it for other jobs, sharing that, because we can have a situation where, for example, several backup jobs are currently running, spooling data to the storage area here, and some other backup jobs are currently writing their data to tape. So we need to have something which can handle concurrent reads and writes at random locations overall, if we're sharing the file system with different spool files, which can give us really good and hopefully guaranteed throughput when reading data sequentially, and can still cope with incoming data to different files, potentially files coming in of different block sizes and all of that. And that is usually something that needs a particular setup. Keep in mind, this is strictly temporary data. None of the data we put in a spool area should be considered to be persistent, which means in the end, we want a fast system. We do not need redundancy, and we need capacity, lots of capacity. Usually. So today, that means you just go for a number of NVMEs or SSDs put into a stripe set. Before, well, solid state storage became very common. We ended up recommending to put together a spooling storage system with as many disks as you could afford, spinning disks. Striped, because that was the only way to really ensure that you get the needed throughput guarantees. It's a bit simpler today. On the other hand, as tape systems also got faster, it turns out that the storage capacity you would need for spooling is still technically and accordingly financially a bit of a challenge sometimes. We have at least, well, we have in the bacula community, there's one user who's been very outspoken about that. And when discussing the requirements with users, he was usually saying that you just need to get a few of the fastest NVMEs you can put into your server system where you have your tape drives attached to. And when people complained that that was very expensive, his reply was usually something along the lines of, if you can afford a tape library, you should be able to afford essentially more or less the same money to be spent on spooling space, because this is what you need to actually get the advantages of your tape library. And while that is put bluntly and potentially a bit extreme, it is essentially correct, because if you want to make use of all the nice expensive hardware you have invested in with the tapes, it is really useful to invest another serious amount of money into hardware to make sure that you get all those results in the end. So if your boss tells you that he's not happy to hear that after he spent money on the tape library, he has to spend another few thousand bucks, whatever those bucks in your currency are, on NVMEs, just tell him that otherwise he will not get the results from the tape drive he wants to see. So that is what we need. The question that you asked in the chat was the size. And this is particularly important, of course. The general idea here is to have as much as possible. You can't do anything wrong. In practice, of course, it is quite useful if you have the capacity you need for the largest jobs you will ever run in parallel. Sometimes that is hard to predict, and very often that is not something you can do. I mean, we have customers backing up their primary storage systems where the backups are essentially petabytes in size. And of course, first of all, they rarely do full backups of that. Secondly, being able to spool the complete thing before putting it to its final destination would be, well, seriously over the top and unnecessary. So in practice, a good amount of spool capacity you want to go for is the added size of all the tapes that you can write to at the same time. So for example, if you are using a tape library with 4 drives, and you expect that each tape that you write can hold, let's say 12 terabytes, then you would probably be well advised if you can arrange for 48 terabytes of spool capacity. And again, this is something we are quite aware. This is a best possible solution. That is not necessarily what you can have. Most of the time, you just go for what you can have, whatever it is, and then have to make sure that you are making decent use of that, making compromises, which is reasonable. And to do that, to actually help the storage daemon, who's eventually responsible for that, help the storage daemon making the right compromises, we have those settings for the maximum spool size and maximum job spool size settings. What it comes down to is if you have a dedicated storage system, a dedicated file system for the spooling area, of a given size, you want to set the maximum spool size to something slightly below that size. Because just to avoid that you really have a file system which is filled to the last byte, to the last block, because that will make things slower if you get to that point. So imagine that we have that we have a spooling area of let's say 16 terabytes. Then the maximum spool size could probably be something like 15.8 terabytes in size. That would be reasonable. The maximum job spool size, in turn, refers to the capacity that each of those jobs that are currently running, potentially in parallel, can use of that spool size. And here it's again a bit tricky. You need to balance things. It's about helping balancing things that you do those settings. If you want to make sure that that all jobs can use the same capacity, of course you would. In my example here, we have 15.8 terabytes of spool size allowed. Four jobs running in parallel, for example, would mean we need 3.9 or something terabytes spool size per job. However, in most cases, that would probably mean that you are not using all the capacity because most of your jobs are probably going to be smaller. So it is perfectly feasible to have for the maximum wait, where is it? For the maximum job spool size to do some overcommitting. If I have 15.8 terabytes overall and I want to run 4 jobs, I could go for a maximum job spool size of like 6 or 7 terabytes per job, because not all the jobs will be using the capacity at the same time all the time. We can do that because we still have the storage daemon adhering to what it actually can do, which means if the storage system is full, we just stop spooling data and start despooling data. Similarly to what we reach, what happens when we reach the maximum job spool size. When any particular jobs ends up with a situation where it could still receive data, but the storage capacity it is using is exceeded, it will just stop receiving data for spooling and will start despooling data to its final destination. So we can overcommit here. The most annoying thing that can happen is if you end up with a situation where, for example, you have 3 jobs, in our example here, 3 jobs which are not limited in spool size, and they make use of all the maximum spool size. And then you have a 4th job starting, and that job could not use any capacity at all. The idea here is to find settings, or to actually just set something which always leaves reasonable room even for individual jobs that get started while everything else is already busy. Nothing dramatic, nothing bad happens if you run out of spool capacity, out of spool size. You will just see that the storage daemon will have to work in small blocks. It will collect small blocks of data and then commit those to its final destination. Essentially reverting back to a use case of your storage that you're using as a target for the for the backups. That will be more or less what you would be getting without spooling. Nothing bad will happen. It will only not give you the benefits of the spooling. Well, and if we were doing this for the benefits, of course, you try to balance things in a way that you get, even in bad situations, in the worst case scenario that you can predict, you still get better results than without spooling. And that could be overcommitting with the maximum job spool size to some amount. It is most of the time no big problem because we can also control how many jobs are running at the same time. So it's essentially really just dividing the available capacity that you have in your spool directory and that you have limited with the maximum spool size, dividing that by the number of jobs you want to start at the same time, and then round it down to have some headroom, or round it up to get some overcommitting if you are expecting all jobs are not running identically fast. In the end, and that is coming back to a question you asked earlier, Yongju, in the end, you are eventually needing more raw capacity for your backup infrastructure. And also, I mean, we have to put every byte into the spool area before we put it into its final destination. So we need this extra capacity. It is not necessarily doubling the capacity, because we know that most of the time you will have much less spool capacity than you have actual backup storage capacity. So it will be a bit of overhead. It will be far from doubling the capacity, the storage capacity used. It will also, and that is in practice more relevant, it will also slow down each individual job in the end, because, well, in the end, we need to write every byte, not just once, but twice, and read it in between again. So obviously this is going to be slower overall. For each individual job. However, if you are running more jobs in parallel and have them better decoupled from storage backend requirements, from network bandwidth limitations on the ingestion side, then you may easily find that in the sum of your jobs, everything happens more more smoothly, faster, and in particular makes better use of your hardware than if you are not spooling. Um, you can, of course, skip the spooling thing. You can just, if you are not configuring that, no spooling will be happening. Spooling needs to be explicitly configured, and it also needs to be explicitly enabled for each job. It is perfectly reasonable to have spooling only enabled for a subset of your jobs. Very often, we find, for example, that if you're backing up to tape, um, you can back up full backups to tape directly without needing spooling because you can read those full backups pretty fast. There's no search time going on. We're not looking at files to actually back up. We just read those and send them in bulk to the storage destination. So having full backups running without spooling is perfectly reasonable, and only run incremental backups where essentially most of the time is not spent moving data, but just finding data to back up. You can run those with spooling. You would be doing that again by using job overrides. In that case, we have one override for the scheduler, which is spool data equals yes or no. And just turning this facility on when needed. And of course, having spooling enabled for tapes and not for disk storage, for example, even if those different storage systems are handled by the same storage daemon, is perfectly reasonable. And keep in mind, if you just use the default configuration and add your devices and do not tweak them in any way, spooling is not going to happening because spooling needs to be explicitly turned on before it happens. If you do use spooling, however, keep in mind you should be having a dedicated file system as the spool directory, backed with dedicated hardware, just because it just makes most sense that way if you are really using the high throughput storage backend for that purpose. It should definitely be a dedicated file system because we want to keep this spool data away from the operating system and logging disk and whatever. We do not want to fill that. And also, if you are doing spooling, I mean, this happens on the storage daemon host, right? But if you are doing backups of the storage daemon host as well, which we think you should be doing, just make sure that you are excluding the spool directory. Because backing that up, whatever is in here, and spooling it again is not going to be very useful in the end. And also, by default, the spool directory, if you do not explicitly configure that, refers or is going to be the working directory of the storage team, which you have to have configured. But that is not a good location. You should definitely put it somewhere else. For different reasons, because one of the reasons, of course, is the working directory can easily be on the same file system as all the other storage daemon configuration. And also the working directory is going to be the directory where the attributes are going to be spooled as well. You heard about that yesterday from Alexander, that when we spool data, we always also spool the attributes, the metadata the storage daemon has to gather and collect. We essentially have to because we do not know about all this metadata before we commit the data to its final destination. The storage coordinates will only be known when despooling, so we cannot have them beforehand, of course. However, if you end up exceeding the capacity you need for the metadata, jobs will fail if we cannot spool metadata anymore. And of course, this is not what we want to achieve. On the other hand, we want to fill the spool directory. So if you have the spool directory shared with on the working directory, you can easily end up in a situation where you do not have enough headroom for the metadata, for the attribute spooling data. And that is something you should avoid. Yes, by default, the working directory is opt bacula working, but let me page up a few pages here. This is something you can configure. So the opt bacular working entry here is a configuration default, but you can change it according to your needs and requirements. Probably something to do carefully and rarely, but if you want to, you can change it. Anyway, this much about the spooling. Do you have more questions about that? If not, I am going to look at some other directives, mostly again about particulars for tape systems. A good deal of that is something you do not need and definitely do not need to memorize because today's tape systems are pretty easy in that respect. They are well standardized. We only have LTO. We have IBM's own native tape technology, the IBM Jaguar technology, and not much else. And all those things are very well specified and have reliably and predictably pre-configured drivers. So you do not need to take too much care about all the details. But if you are using very specific tape systems or have to handle older technology, it is probably interesting to understand that you have ways to configure all the details of how Bacula interacts with tape drives. Back to the point that we can configure that if Bacula or if the tape system can do block positioning, forward, backward, which is the forward space record for and backward space record settings, for example, and all those specifics that you may want to set. You shouldn't be needing that these days. We have some other settings which may be important, in particular for standalone tape drives that are not part of a tape library, but are just attached to one of your systems, where the important thing is that you need people to change tapes, which means you introduce, well, first of all, potentially delays that are not easily controlled. And secondly, you introduce the risk of people just doing wrong things, inserting the wrong tape, not the one Bacula asks for. And that you may end up with a situation where people are responsible for changing tapes who should not be responsible for operating the Bacula software. In particular, we have ways to do that where we can make sure that you get, we eject the tape. Somebody has to change tapes, but we will not know which tape is in there. We will, and we do not know when it will be in there, in which case we can configure Bacula to automatically check if it finds a tape, and if there is a tape, see if we can use it and go on or do something else. So you can actually operate Bacula in that way. We have seen that a few times in remote offices which needed tape backups for a variety of reasons, but didn't have IT staff on site. In that case, you could essentially set up Bacula in a way that it was reasonably usable by office people. So those are things you can do. Very particular. You shouldn't be doing that very often. And we have one set of settings here, minimum block size and maximum block size, which is really, really important to be set up once and not touched afterwards. Well, the block sizes are essentially the limits of the data blocks that Bacula will write to a tape. However, when reading from tape, we need to know what block sizes we have. We need to know the amount of data read per block up front because we need to tell the operating system kernel how many bytes to read. Also, we usually need to tune the block size for good throughput. Tape drives are fast when you write blocks of a size they can properly handle. And as we have, well, block headers and checksums and inter-block spacing and all those overhead between blocks, the tape usage capacity and the tape throughput get better if you have larger block sizes. There are, however, some limits. You cannot just make them infinitely large or as large as you like. Again, because we need the granularity, we need to have predictable block sizes. And the tape drive itself needs to handle those blocks. So there are, for each tape drive, for each tape technology, there are block sizes that the drive can handle best. with best throughput, with best compression throughput, with best tape capacity use. And you need to know those and you need to configure those because they are essentially depending on what you want. They are not strictly hardware defined and limited. So what you need to do when you deploy new hardware is you need to decide on a block size you want to use, configure that, and hopefully not change it. If you change particularly the maximum block size configuration for a device, you may have problems reading tapes that were written with a different block size. So to avoid that, our recommendation is you do some testing up front to determine what the right block size is. With today's tape drives, the minimum block size would usually be 0. Of course, we never write 0-byte blocks, but that essentially tells Bacula that we can use variable block sizes up to whatever is configured as the maximum size. And we try to write full blocks whenever possible. So the idea is to find the proper maximum block size. You can do this very carefully and thoroughly with the test routine. We have tool to do that and a process to do that, or you just use rule of thumb, and that is with today's tape hardware, you use 256 or 512K maximum block size settings and will get decent results. And after you set that, you are not changing that. If you change that, you may end up with a situation where you have to come up with a particular migration scheme for old data on tapes, which is the most annoying thing. The second most annoying thing is you may end up with essentially keeping track of older volumes. Well, Bacula does that in the catalog, but you need to understand that you can only use older volumes in particularly configured devices with Bacula. That is annoying. It is possible, but you should be avoiding that. To avoid all that extra hassle and overhead, set the right maximum block size and do not change it afterwards. Very simple. If now you get curious and you get nervous, if at this point you find that you want to change those settings for your existing backups and you have tapes that you want to be able to restore from, written with what you have now, please do not just blindly change that and hope for the best. Ask our support, you're all Bacula systems customers, so ask our support on how to handle that. We have ways to help you making the right decisions and doing the right things. And we have some other settings for the device direct or for the device resources in the storage daemon, which we hope you will not be needing and using. Particularly those things like free space command and mount point and write part command, they are legacy configuration items intended to be used with optical media writing, which we started phasing out. Essentially, the code has been partly removed from the Bacula Enterprise software. And we did that because it was never leading to reasonable, reliable backup regimes. That we supported that was a fault in itself. The personally most annoying fact here is that it was introduced because I wanted it on behalf of a customer of mine at that time. It turned out that was not a good idea. So if I see stuff like mount command and mount point in your storage daemon configuration later on, I will be very disappointed and slightly embarrassed. Spare me that and do not use it. So that was more about tape devices. We are coming back to putting together devices in tape libraries and auto changers with Bacula, where we group devices under one common name in a way. Very important, strictly required if you want to make use of a physical tape library, and very strongly recommended to do if you're writing to file-based storage systems. So we have this this representation of those things as we call it as auto changers, where we can essentially automate media management. And we can, that is in reality at least as important, we can group more devices into an auto changer. So essentially we can tell the bacular job, that is what we are interested in here, to just write to an auto changer. And which actual device, which drive gets used is something the storage daemon, with a tiny bit of help from the director, will sort out. So it is easier. It gives you more flexibility and less micromanagement of your devices. For that to work, inside the storage daemons configuration, we need an auto changer resource. The director storage resource, which we configure in the jobs eventually, will then refer to the auto changer on the storage daemon end. It will point to that name, not to the individual devices. And inside the storage daemons configuration, the auto changer resource will essentially consist of a name. Everything needs a name, and of course we need that one to refer to it, and a list of devices, and a bit around that. But these are the interesting and really critical things, where each device is just the name of one of those particular devices that you have configured. What you also need as additional device configuration is that you need what we call the drive index in the device configuration, which is essentially just the index number of a tape drive in the tape library for the physical libraries, and just an index number which you create by counting up from 0 for the disk-based devices. On top of that, well, this is an example here. On top of that, of course, the thing doesn't need just the name and the device. I mean, those are important, of course, but we also need to make sure that we can control the actual auto changer. So we also have a command to run to actually do something with the auto changer, such as moving tape cartridges in a tape library. So this is additionally needed or useful, but here the most important things are, of course, we have the name for the auto changer, and we have the devices it uses, and the devices are just the references from the auto changer to the particular device resource by using the names here. Here we see, well, of course, the other drive as well, and we also see the drive indexes counting from, well, 0 for the first one up. Those devices, they should share the same media type, because that's part of the idea that any tape we have used in one of those drives can be used in either of them. That's part of the magic, of course, part of the flexibility that we have. So those settings here, those directives here, they are giving us an idea of what we can do with an auto changer, what that looks like. On the director side, we would point our storage to the LTO changer and not to individual drives. So this is all we need here. Kind of straightforward. But we can have it a bit more complex, but we are not going too much into those details here, because we can actually have tape libraries with different tape generations in there. Not uncommon with LTO, where we have pretty continuous development and limited backwards compatibility. So essentially that means if you have an LTO8 drive and old LTO4 tapes, you cannot read them in the old drive, but you may probably want to keep your older tape drives as well. To do that, you can end up with a single physical tape library with different generations or even technologies of tapes. That is something that can happen, and that is something you can represent in the storage daemon configuration. Bacula can work with those setups. You can also have a situation where one tape library is controlled by more than one storage daemon. We call that shared storage. It's something we can do. We have an additional piece of functionality, which we call our shared storage plugin. The name is pretty boring in that context, which is a plugin to the storage daemon, which essentially ensures that the drives can be locked against use by other storage daemons at the same time. And we can have a situation where we can have one physical tape library partitioned into several logical tape libraries. I mentioned that before. This on the bacula level, on the bacula side, is actually something we do not need to care about. We just need potentially longer timeouts. So we can have pretty advanced auto changer use cases. However, they all need to be represented in a particular manner because what we need to operate the tape library may need to be adapted accordingly. The changer device, for example, and in particular, is the device node on the host that we use to control the tape changer. Not the tape drives, but the mechanism that moves tapes around. So that is something that can be interesting in very particular environments. Most of the time, it will just be a pointer to a device node like dev tape by ID, or depending on what you use on as an operating system, could be dev RMT if it's a Solaris system, for example. If you specify that in the auto changer, you do not need the respective configuration in each tape drive or device configuration as well, to simplify things. But, and this is important, if you have the changer device, and very similarly actually for the changer command, specified inside the device resource, which you can do, that device specific configuration will be used. So you can override in a way the default that you have for the auto changer. And this is actually one way we can handle tape auto changers, which actually mix different technology and potentially even distinct hardware in one group of devices for bacula to use. Well, so this is the device node. We have the changer command, which is just one of those specifications to run a program with certain parameters, and the parameters usually are provided as those percent encoded variables, which then get substituted with things like the changer device configured. We have an example for that. I don't actually know if we have an example here. No, but it's pretty straightforward. And the nice thing is, in most cases with regular tape libraries, what we provide as a default configuration, or rather as an example, will just work without you having to change anything. The default that we use is is called an MTX changer. It's a script file which uses behind the scenes the MTX program to do the actual work, and some helper tools as well. But keep in mind, this is a configuration item. You can change the command, and you can actually change the program you use as needed. I have a long time ago been working with a customer who had a particular tape library where the only way they could operate the tape library was through the web interface for particular and rather annoying reasons. So we ended up creating a changer command that used curl to operate the web front end. You can do that. It gives you flexibility, but most of the time you will not have to change the defaults. So much about that. Just to conclude this, we can also put non-tape devices into auto changers. Usually, and we are seeing that even in the default configuration these days, you would be doing that with disk devices, where we use what we call the disk auto changer. Can be pretty nice because it gives you all the flexibility you want without having to do all the micromanagement. If you want to make sure that you are loading your storage systems properly, have different jobs running in parallel, all using different pools, and you do not want to have a relationship of one storage device for each of your jobs. So you can do a lot using things such as this one. Here we have an example configuration again on the storage daemon side. Here we have a file changer, so an auto changer being used with file-backed devices. We have, in this case, the convention to use a changer command, which is an empty string, and a changer device, which is def null. That essentially tells the storage daemon that actually media changes are happening by just accessing files. Of course, we can do that with files because they are just there. And we have a device list of 4 changer devices. Of course, you can't write it like this. I had to use a shortcut because I would be running out of slide space otherwise. And the actual devices would be looking like that, all identical, just a different digit here from 0 to 3. They would all point to the same archive device because we want them all to be able to share their media, and they would all be configured identically, essentially. On the director side, we point our jobs to this storage, and keep in mind those are names we make up. So it's our arbitrary decision what to use here. So internally in the director, we use this storage auto ch-file1. That storage is defined here with that same name, and it points, well, to the auto changer itself. This is merely the same thing in this case, but the device we use is called file changer 1 on the storage daemon. I mean, I have abbreviated that, but this is the name we send to the storage daemon, and this refers to the storage daemon's auto changer. So this is what needs to be aligned. That we are seeing a different name on the director side, this is an arbitrary decision. I wouldn't do this in practice. In practice, I would use the same name. But here, for illustration purposes, this does not need to be identical. That's names we make up. So it's our choice what we do here. Well, and in the end, each individual job would, in this case, kind of inherit the storage to use. This one, which would essentially point through the different layers of abstraction eventually to one of those devices here. But we do not need to know which one. We do not even need to know on the director side how many devices we actually have. Here we have 4 devices, each of them allowing one job. So obviously we can only run 4 jobs at the same time. The director, as you see it, doesn't even know about that. The director would be allowed to run 10 jobs at the same time, which would mean the director just sends commands to the storage daemon to run 10 jobs. The storage daemon would accept that, but it would essentially put 6 of those jobs on hold. They would be queued. And we do not have to do all that management ourselves. We just put reasonable defaults here, and director and storage daemon will then eventually do something reasonable with what we have configured. And that is essentially the whole point of putting disk devices into disk auto changers or virtual auto changers, because we do not have to care about the details afterwards. We just look at the big picture, have some limits here, point our jobs to certain storage, don't care for the details. That's the idea of doing storage auto changers with disk devices. So the question, of course, in a single device, we will always be using one archive device here. However, if you think about this, this means the bacula volume is created in this directory. It can only be accessed with devices that have this archive device configured to point to this directory. As we want the flexibility to use whatever actual device we have, not having to pre-configure that this particular job always writes to device 0, we need to make sure that we can find our volume, no matter which device we use. And that is that by making sure that we have the same archive device for all the devices that actually should be sharing the volumes. And we do this because this allows us to make sure that, for example, we can run an arbitrary number of jobs at the same time. We can also read and write through different devices at the same time to the volumes stored in this archive device directory. And that we can, for example, control that we have only one job running at those things at the same time. With a setup like this, we would also ensure that all the job data that is in one device is always kept together. We do not interleave data. And we can still run parallel jobs ending up on the same storage device. If we just had one device and we sent all our jobs to the same device, and the same archive device and all of that, well, we could run our backups in parallel. We would be interleaving data. No problem there. But interleave data means that when we restore data, we have to skip over lots of data. We are wasting time when restoring, when we are using interleave data in volumes. It also means that when we expire one single job, we may not be able to expire the complete volume because there may be data that is still valid on the volumes. If we are using disk-based storage systems where we can arbitrarily create devices, they are essentially just configuration items, they are coming for free. It is a reasonable idea to make sure we end up with such a setup here, because it gives us flexibility without introducing new limitations or restrictions. We just gain functionality without having too many drawbacks here. And to do all that, to achieve all that, such sort of a virtual changer system is usually the right choice. Does that answer your questions? Or, well, the other way around, if that, wait, you have something. So the maximum concurrent jobs number, no, it does not strictly rely on that. As we see in this example, I have one concurrent job, one single job per device. I have 4 devices in the auto changer, so the storage daemon will only allow 4 devices implicitly passing in a way through this auto changer. On the director side, I have the maximum concurrent job setting set to 10. This is coming back to what I said in the earlier part of the session. Try to put the actual applicable limits where they are actually making most sense and keep the flexibility at all the other points. And here, assuming that the idea there is that we have one job per volume only, to prevent interleaving and to have the granularity when recycling storage capacity. Of course, the maximum concurrent job setting of 1 per device is reasonable. It is kind of required for this setting, actually, for this goal. At the storage daemon globally, we don't see this, but keep in mind the default would be 20 jobs at the same time. At the director side, configuring 10 jobs is perfectly reasonable. Well, we will have jobs queued, but we will not have too many jobs queued. We just a few of them. If we start more than 10 jobs using that storage at the same time at the director would be knowing, okay, 10 is fine. I send 10 jobs off to the storage team, but everything else the director will put on hold. It will queue them. They will be waiting on the director end. A few of them will be waiting at the storage daemon. They will already be reserving resources, for example, on the director end, but they would not be using resources on the storage daemon at that time. So we have a certain flexibility here. And of course, if we do that the other way around, maximum concurrent jobs equals 1, for example, at the director end, of course, we would have 3 devices idle all the time. That would be pointless, but it wouldn't be doing any harm. So we can actually do some sort of preparation here. I tend to do that if I'm setting up bacula instances where I do not know how fast they grow and what we can do with the hardware. Configure a storage daemon having 20 devices like this. I mean, it's just configuration, no problem. But do not use 20 devices at the same time. Start slow. Have maximum concurrent jobs equals 10, for example, here. Okay, I know I have not made use of everything I pre-configured, but that also means if I find that over time I need more devices, I can just increase the setting, the configuration at the director side. I do not have to restart the storage daemon for that purpose, for example. If, on the other hand, I find that 10 jobs at the same time is a bit too much for my network capacity, well, then I just decrease it over here and I don't have to restart the storage daemon. Well, if I want 10 jobs at the same time, in that scenario, I would just start creating more of those devices, up to 10 in that case, for example, probably more even. As I said, no problem doing a bit more, just preparing devices I know I won't need. Actually, just if I know I want to have 10 backup jobs in parallel, I would actually go and create like 15 of those devices. Configure them accordingly. Well, I have a few spare ones, but that's fine. I may need to restore even while I'm running 10 backups, and I would have the device for that immediately available. So just preparing a bit more than what you need works quite well if you can put the limits you want to be applied on the end where you can flexibly change it. That is the director side, of course. So I'm trusting that that covers this disk and storage auto changer aspects. So I would, at that time, I would say let's start the long lunch break. We will be doing more presentation in 3 hours. In between, I will be here for the next, what is it, regularly 43 minutes for any other questions or discussion or help with whatever you need. And I will also be back in 1 hour after that. So the usual thing, 3 hour break in between with, well, officially 3 hour break with 1 hour of optional discussion and question time right now, and 1 hour before we continue with the presentation. Okay, and to make that clearly visible, I will add that annotation here as well. Wait a bit. Let me start with the annotation. I will forget that otherwise, and then come back to this one. So it would be 12 CEST. And so hopefully that is clear. Angola minus 1 hour and Korea plus 7 hours, I believe. I hope I got that right. I'm terrible with time zones. And now coming back to the question, yes, if you have a single backup directory, well, the single archive device, obviously. Yes, you can control the number of parallel backups by adjusting the number of devices. But keep in mind, it's can. It's not the only way to do that. And it works quite well with tape. Sorry, with disk, as you imply with a backup directory. With disks, it works very well because the devices are coming for free. And just having each of those devices configured with one job at the same time is also reasonable. Well, and if you want to just configure that on the storage daemon side, it's perfectly reasonable to do that. It will work. Adding another limit on top of that, essentially at the director side, just gives you another knob to turn, and in particularly to turn without having to restart the storage daemon.